Picture a pond with a curvy, wandering shoreline. Someone asks a simple question: how much surface does it cover? There's no neat rectangle here, no tidy circle, just a shape that refuses to sit still. And the way we finally pin down its area turns out to go much further than a pond. So let's start the way you might if you only had a ruler and some patience. Straighten that shoreline into a curve on a graph. The area we want is the region trapped between the curve and the line beneath it, from one edge to the other. Here's the trick: cover that region with tall, thin rectangles. Each one is easy, just width times height, and you can find its area in a heartbeat. Add up all the rectangles and you get a pretty good guess for the whole area. It's rough though. The flat tops poke above the curve and dip below it, leaving little gaps and overhangs. So what happens if we stop settling for a guess and make the rectangles thinner? Watch. 4 rectangles, then 8, then 32, each batch narrower than the last. The jagged staircase presses closer and closer to the curve, and the gaps shrink toward nothing. Push that idea all the way. Infinitely many slices, each infinitely thin, and the guess stops being a guess. It becomes the exact area. That endless sum has a name and a symbol, the integral, written as a long stretched s from a to b of f of x dx. And this isn't only about ponds. Draw speed against time, and the area underneath that curve is the distance you traveled. Same slices, same sum. Area and total accumulated are really the same idea. But adding up infinitely many slices sounds exhausting. Is there a shortcut hiding underneath all this? There is, and it's one of the most beautiful results in all of mathematics: the Fundamental Theorem of Calculus. It says that accumulating area and measuring a slope, integration and differentiation, are exact opposites. Building the area up and finding how fast it grows undo each other. That link is the shortcut. Instead of summing forever, you find an antiderivative, a function whose slope is your curve, and just subtract its value at the two ends, f of b minus f of a. That's a definite integral, a single number. Leave the ends off and you get the indefinite integral, a whole family of functions, plus a constant c. From the area of a curvy pond to the distance under a speed graph, it was one move all along. Slice something into infinitely many pieces and add them back up. That's integration, the art of accumulating, one vanishing slice at a time.